In this video, we're going to look at the definitions regarding information about extreme values of functions and graphs. So before watching this video, be sure you finish off that preliminary example to get you ready to focus on these types of concepts dealing with graphs and functions. So let's get started on the definitions that we have here. So in these definitions, we're just making rigorous or formal some ideas that you just thought about in the preliminary example. So for these definitions, let's let f of x be a function whose domain is D. That means the input values into f are coming from a set D. So we have this notion of an absolute or global maximum of f on D. It occurs at a point x, call it C, if f of C, rather, the output at C, is larger than the function for any other x value. And if you take a moment to pause and reflect on this one, you can see that this definition makes sense for what we'd want to be an absolute or global maximum. In graphic terms, this value is the highest or largest point on the graph of f of x. So it's the overall absolute global maximum. Similarly, we have a notion of an absolute or global minimum of a function f on its domain. And it, as you might guess, occurs at a value, call it C, such that the output of our function at C is smaller than or equal to any value, or smaller than the output value for any value in our domain. So visually, this would be the lowest point on the graph of f of x. Awesome. Okay, so those are global or absolute maxes and minimums. We also have a notion of a local maximum and minimum. So a local maximum of f of x occurs at a point x equal to C if f of x, or f of C rather, that output value at C, is larger than any output value for x near C. So visually, we might have a graph with several ups and downs. And we'd say that this point here in our graph, that's a local maximum. Because if we look near that output value, so let's call this C, just using the language that we just used. Here, this is f of C. If we look near C, the outputs of f are all smaller than the outputs of f at C. So that's what we call a local maximum. In other words, if we zoom in at that point and we didn't know anything else about our graph, we'd say, heck yes, that's a maximum there. Okay. And maybe if we want to write this down in words a little bit, so we have a local maximum at a point if f has smaller function values on either side of the output at C. So we could say f has smaller values on both sides of C. All right, then similarly, we have a notion of a local minimum, and that occurs at a point C if the output of f at C is smaller than the output of our function for any values near C. So visually, what does that look like? Well, we could look at a similar graph here. Oops, let's start again. So if we look at, say, a point C here, if we zoom in, we see that our function is smallest at f of C if we look near C. So just focusing around near C, it's okay that we even go lower over here. That doesn't prevent this point from being a local minimum. So visually on the graph, what does that mean? That means that f has larger values on both sides of C. All right, so take a moment to pause the video, make sure you have all those definitions written down and maybe highlighted. And these definitions so far have been pretty intuitive. Now let's get into some other definitions of some words that might be new to us, but are still related and relevant to these notions of minimums and maximums. So our next definition here is that of a critical number. A critical number of a function f is a number C in the domain of f such that either we have the derivative at C is equal to 0, or the derivative at C does not exist. And the reason why this point is a critical point on the graph, as you might have guessed, is whenever we're in this situation where the derivative is 0 or does not exist, then that means we either have a horizontal tangent line, as we see in our graphs here, or kind of a notion of a vertical tangent line. The derivative doesn't exist. So there's something special that happens there in our graph. Now, I just want to keep in mind that it's not always the case that we have a max or a min at that point. For instance, if our function looks something like this, then here in that center, we have a horizontal tangent line or a critical value, but we don't have a max or a min. So we call critical value a value in the domain where the function's derivative is 0 or doesn't exist. Our next definition here is that of an inflection point. So a continuous function f, continuous so that we can take the derivative of it, has an inflection point at P, f of P. So that's an output, that's a whole coordinate on our graph. If P is a point in the domain of f at which the concavity of f changes from either up to down or vice versa. All right, so now let's just take a quick moment to look at some of these definitions in action by re-looking at that preliminary example. So here's our graph in the preliminary example. And recall that in this graph, we're measuring time on the horizontal axis, and then the heights of a tide in feet on the vertical axis. So then first, let's identify the global or absolute maximum and minimum values. So we see that on this interval from 0 all the way to 21, that our lowest point, our lowest tide occurs at midnight. So here, this first point would be the absolute or global min. Where does the highest tide occur? Right here at about 17.5 hours. This would be our absolute max or absolute maximum. Then, so what about local minimum? Well, here, we can look for minimums, a valley or a lowest spot in our graph. It's maybe not the lowest, but lowest in a region near the point. So we have this dip here at about maybe 11-ish. This would be a local minimum. Any local maximum? Yeah, right over here, we have a peak in our graph. It's not the largest peak, but it is a peak. So here we'd have a local max. And now one thing I want to mention is that even though we have some absolute min and max, these are also considered local max because they still satisfy the condition that in a region or area near that output, this value is larger than any value near it. So it's still considered a local max as well. And similarly for this absolute min, it's also a local min. Okay, that's just kind of a small point. And now for inflection points, we're looking for where our function changes concavity. So if we follow along, we can see that we are concave up here, And somewhere we switch to concave down along this line I just drew. So if we kind of estimate carefully, we can see that that kind of occurs maybe around here, maybe around 2. So here would be an inflection point. And we can continue along our graph and identify some other inflection points. There we go. All right, so in the next video, we're going to continue our work on this page on information about extreme values, and we're going to look for some tests for determining when we have maximum, minimums, and inflection points.